Final function that you need to deal with today is the update flight function. Now if you look here, this is a function that's on the Dart itself. So once we fire the Dart, this function gets called every single frame. A frame is like one tick of the simulation. It gets called over and over again to slowly change the position of the Dart as it flies. So for example, we're going to reload here, change the angle. So if you see all these little dots, each time represents a single tick, a single updating flight of the Dart. And we call that maybe about 30 times a second. And that calculates the trajectory of the Dart. So the way to do that is to update the x and y position of the Dart using the velocity that we calculated over here. And then change the velocity itself with gravity. Now remember, gravity is another vector which points directly downwards, and that represents the acceleration on the Dart as it flies. If we didn't do the gravity update, the Dart would just fly off in the same angle that it started off, and it would never hit the ground. Okay, so let's look at the description. This function updates the path of the Dart. It's called every frame of the simulation. So it's going to be called 30 times every single second. The variables you have to access are this.x, which is the current position of the Dart on the screen, in pixels. So right now we're seeing things in meters, right? 0 meters, 2 meters, 4 meters. But there's also pixels, which are, every single little dot. So 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So this entire width of this screen is 600 pixels, and the height is 400 pixels. So in order to actually draw it on the screen, we need to know the x and y position of that Dart, which is what you can access with this.x and this.y. You can also access the velocity vector, which is one of those p vectors up there, and that vector has the properties of x or y for the x and y components of the velocity. Finally, you have access to this meter variable, which represents a way to convert between meters, which is what we're showing over here, and the pixels that are actually needed on the screen. So if you have a this.x position, right, that's in pixels, if you multiply it, if you start off with meters, remember the velocity that we calculated above is in meters. So this.velocity.x is going to have the x component of the velocity in meters per second. If you want to convert that to pixels, which you're going to need, you multiply it by this meter variable. Finally, t represents the number of ticks per second. This is important to think about. Let's say t is 30. That would mean that the simulation happens 30 times, that this function gets called 30 times every single second. So if we want to update the position of the x and y variables, or of the Dart itself, we have to do that 30 times every single second. So if you have a velocity of 10 meters per second, you can't add that to the x and y every single tick, because then you'd be adding 10 meters every 30 times every single second. What you need to do is instead divide it by t. So if you currently have a velocity, you need to divide that by t, which means that we're going to be changing the position of the Dart by 1/30th of the total velocity, so that after 30 runs, that'll be 1 full second, and it'll have updated by the full velocity after that second. The same way, you need to do the same exact thing for the way you apply gravity to the velocity vector. Also keep in mind that since velocity is a vector, you can do this trick here. We can say gravity equals new p vector, which is going to represent gravity. Let's say gravity is 5, for example. You'd say this.velocity.add. It's a special function you can use to add vectors together. There we go. Now we've just changed the velocity based on whatever this gravity is. You could do other things. You could do wind. You could add a wind vector and add that too. And each of these things would change how the velocity of the Dart updates. And then up here, that would update the position. So you need to fill in maybe a couple lines right here and a couple lines right here to update the Dart's position. After that, you'll be done creating the simulation, and you can use it to play around with, to figure out, using the numbers that you collected on Friday for your lab, we can use it to figure out what the actual K constant of the spring is. So just try some numbers, set the height to whatever you measured it as, and figure out what collection of values creates the K constant, or the distance that you measured, and you'll be able to figure out what K constant generated that.